Perfect. So having carried out the QR factorization using Gibbons rotations last time, now we will learn what household reflections are and how they can be used for the QR factorization, and and more about the distinction between the two approaches. So with Gibbons, nice thing about that is it is flexible because each individual Gibbons rotation only acts on one entry. So if your matrix is sparse, or if you're updating QR factorization, Gibbons is nice for that. But for the general case, if you just have some n by n matrix and you want to QR factorize it, Gibbons is not it's reasonably efficient, but it is not the most efficient. So that's the main reason why we're going to look at Householder today. Well, even though I just made that point, I can see where in here I actually mentioned what the operation counts are for the two. Okay, that's going to drive me nuts. I mean, in both cases, it's going to be on the order of mn squared for an m by n matrix. It's just that what's the constant in front of the mn squared. These squares. Okay. Actually, maybe it's something, but I made a homework problem, and that's not in the notes, and that's why it's not showing up in my. Okay. Okay. Okay, so one thing I can say is that to get just R, because there's two things to do in QR factorization. You're reducing A to upper triangular form, and then there's also the accumulation of orthogonal transformations to get Q. But if we focus only on the getting R part, Gibbons is 50% too expensive. Another way of putting it is that the approach I'm going to show you, Householder, takes 2/3, roughly the number up to 2/3 the number of flops that Gibbons takes. So it is. So it's not order of magnitude different, but it's still significant. Just like with Gaussian elimination, if a matrix is symmetric positive definite, okay, it's 2/3 n cubed operations, but you can cut it down to 1/3 n cubed by using a method specifically for symmetric positive definite matrices, LDLT or Cholesky. Okay. So while Gibbons does offer a number of advantages, the number advantage I mentioned last time about Gibbons is parallelizable, whereas the approach I'm going to show you today is not. But then there's this one drawback of Gibbons that's significant enough that I still teach about Householder. No, I'll actually do that. Now, the first I can tell you, first, what is a household reflection? Why we call it that, besides the fact that it's created by Householder, and then how we use it for a QR factorization. So Okay. Now, yeah, in my notes and book, I'm not sure why I'm using the letter capital P to refer to a household reflection when, of course, makes sense to use H. I do that later though.
You use H, but I saw somewhere that you use G instead of an H for householder. I didn't know if that was an error or.
Where?
In
the book?
I was just pulling up the book to see.
Oh, that one might have actually been a mistake.
It's where you multiplying.
Like an example?
No, it was just.
Oh.
I'll find it.
Okay, because that's gonna drive me batty. Because that's something I didn't even know about. I think there's one thing that I might have been aware of already. Oh, no, that wasn't it.
No, it's page 140. It was when you were doing grammar. Minute. H1 to HR.
Okay.
And yeah, and I thought that should have been a different letter.
Oh, I see. Oh, okay, right. Yeah. Okay. Good to know. Oh, we have it right, the rank deficient least squares. Okay, now, why am I even looking here? Okay. Get my notes. All right, so you find a matrix P for some reason. And it's gonna have this form, identity minus some scalar tau times some vector UU transpose. For some non-zero vector U, because otherwise not a very interesting case. Okay. Now, this is called a rank 1 update of identity, because when you have a column vector U, so U, two column vectors U and V, UV transpose is a matrix. That's called an outer product. It's also a matrix of rank 1. In fact, any matrix of rank 1 can be described as an outer product of that form. This one also happens to be symmetric because we're taking an outer product of a vector with itself. So the question is it possible to choose the scaling factor tau so that P is orthogonal? Well, I'm going to point out before I look into that, we just by the form of P that we have here, it's already known to be symmetric. Just because we have U times its own transpose. All right. So to see if it's possible to make P orthogonal, I'm just going to go ahead and compute P transpose P. So that's going to be identity minus tau U transpose identity minus tau U transpose. But I mentioned already P is symmetric, so we're actually looking at P squared. So I can really ignore this transpose here and then just FOIL it out. So we have identity minus 2 tau UU transpose. And then finally have plus tau squared U transpose U transpose. Now, what's kind of weird about this, when you take two outer products and multiply them together, what's in the middle here, U transpose U, that's an inner product. It's also a number. So I can take U transpose U and move it around wherever I want. So both of these terms have UU transpose in them times some scalar. So if I group these terms together and basically factor out the UU transpose, I get the following. So I have tau squared minus 2, tau squared U transpose U minus 2 tau UU transpose. Now, I want this whole thing to equal identity. Therefore, I want this whole thing to be equal 0. And if we could set tau equals 0, but that's not interesting because then P is this identity. So we'll let tau be equal to 2 over U transpose U. So for that value of tau, we can, then P turns out to be not only symmetric, but orthogonal. So this leads to this description of P. Identity minus 2 V transpose, where V is a unit vector in the 2 norm sense. Because this right here, U transpose U, that's the same as 2 norm of U squared. So what's happening here is having UU transpose over U transpose U, that's the same as V transpose, where V is the normalization of U. So I'll just write it this way, with the assumption that V is a unit vector. I said some uncertainty there.
Yeah, I had to take a second to
Okay.
unravel what you said.
Yeah. Yeah. So because the denominator is norm squared, that's the same as U over its norm times U over its norm again transpose. So we just call that V. All right, so this is like the official form of a householder reflection. I guess I'll summarize that over here. So any matrix of this form, identity minus 2 VV transpose, where we assume that V is a unit vector in a 2 norm sense. That is a householder reflection. Now, P of this form is symmetric and orthogonal. But these are odds. You think that there wouldn't be any such thing as a matrix that is both symmetric and orthogonal, except maybe like identity or minus identity. But these matrices do it too. This rank 1 update of identity. So an interesting consequence of the matrix being both symmetric and orthogonal is this: that because it's symmetric, that means P equals P transpose. because it is orthogonal, P transpose is also P inverse. That comes from P transpose P equaling identity. So you put the two together. P is its own inverse, which still just kind of freaks me out. A non-identity matrix being its own inverse. Okay. Equivalently, P squared is identity. Okay. Now, I have not said anything to explain why we call it a householder reflection of all things. But I'm going to take care of that now. All right. That's an example. I'm gonna let V be equal to a vector 1, 0. And I'm gonna let X be a vector 1, 2. So now I can work out what P is. Okay, so that's going to be identity minus 2 B transpose. We do now a product of two vectors. You get a matrix where each element of a matrix is just the product of an entry of this times an entry of this. So what we get is the identity. So 1, 1 entry is first entry times first entry. The 1, 2 entry, first entry times second entry. Second entry times first entry. Second entry times second entry. So, and we can see that's a rank 1 matrix because we only have that one non-zero entry there. And then we complete the arithmetic. So it's just identity except the 1, 1 element is negated. So P times X is just going to negate the first element of X. So whatever, so this is what P would do in general to any vector you apply to. It's just gonna negate the X component. That's relevant because what is V here? It's the vector corresponding to the X component. Like they're pointing the direction of the X axis. On the other hand, if I let Y be the vector 0, minus 1, then Py, well, you negate the first component, but there is no first component, it's still 0. So Y is not changed by P at all. Now, more generally, I have any vector x, there is a unique decomposition of x into a scalar times v plus another scalar times, I'll call it z, where z is orthogonal to v. This is what's called orthogonal projection. So actually, I can tell you what the constant C1 is. C1 is equal to B transpose X. And C2Z is just a vector X minus BV transpose X. This right here, the matrix VV transpose, that is the projection onto a subspace that consists of all scalar multiples of V. So this is something you can do in general. There's a unique decomposition of a vector within a certain subspace and another vector in the orthogonal complement of that subspace. So I'm using this decomposition to show exactly what P does to a vector. So Px is equal to P times first term plus P times second term. Then I fill out what P is. So P is identity minus 2VV transpose C1V plus, actually, I'm going to pull the constants up front because I don't really want to deal with them anyway. D2 times identity minus 2VV transpose Z. V transpose Z is 0. So the second term turned out to be C2Z. It's unchanged. So P doesn't touch that part. As for the other part, what we have here is C1, and I can take the V and distribute it through here. B minus 2B V transpose V. But V is assumed to be a unit vector. So this scalar here, V transpose V, that's 1. So we're left with V minus 2V. In other words, minus V. So we get minus C1V plus C2Z. So that's what P does to a vector. It negates the component in the direction of V, leaves all other components that are orthogonal to it untouched. Another way to describe it is geometrically, P reflects X across a plane that is normal to V, thus negating that component. We can see that from this example here. Here, V is pointing in the X direction. So But what happened with this vector here, the x component got negated. In other words, the vector, if I draw this, we had 1, 2 originally. So this is x coming from the origin. And then px is over here. It got reflected across the y-axis that is orthogonal to v. Questions so far from anyone viewing, whoever they are? Okay, so now we want to try to use this kind of matrix, knowing what it does, to zero entries in a matrix as part of the QR factorization. We're still trying to reduce the matrix to upper triangular form. So the way we'll do that is so we want to choose B. Well, actually, I need to rephrase it differently. Okay. Given some vector x. That's important. Yeah, that part. Choose V. So that, and when you sticking with the assumption that V is a unit vector. So that Px, which is still defined to be identity minus 2 V transpose times x, is equal to some scalar alpha times E1. E1 is the first column of identity. So it's a vector, all zeros of a 1 except for a 1 in the first position. So if you think of X as representing like the first column of a matrix you want to reduce to upper triangular form, that's what you want to do it. You want to zero everything below the diagonal. So this household reflection, if we choose to write V, can do that all in one fell swoop. And bam, first column's done. Then if we move, then we can move to the second column, and then we'll be dealing with a vector X that has one entry less. It's the second column except for first entry. So from a diagonal entry on down, we'll do another one of these and wipe out everything below that diagonal entry and keep going. So that's how the process is going to shake out. But now as you can see how we choose V to make that happen. Now, because P is orthogonal, and remember, multiplying by an orthogonal matrix preserves the 2 norm. So the 2 norm of this vector, alpha E1, has to be the same as the 2 norm with X. So that tells us that the scalar alpha must be equal to plus or minus the 2 norm of X. And we'll figure out which one, plus or minus, a little later. Okay, so if we write out what Px is, all right, so we have identity minus 2 V transpose X. Whoops, X outside the parentheses. But I set it equal to alpha E1. Then I distribute X through here, so X minus 2V, and then V transpose X is a number. equal to alpha E1. So then if I rearrange this, okay. Yeah. Then I end up with 1/2 x minus alpha E1 is equal to B transpose X times V. Now in the notes, I go from here to have this real long nasty sequence of algebra to get the formulas for the entries of V. But to really see what V is, you actually don't have to go through all that. Really, the key equation is this equation right here, because of the assumption that V has to be a unit vector. So this vector is a scalar times V. So but what it says, that this equation says that the direction of V is the direction of this. So really, all we'd have to do is take this vector here and normalize it, and then it's either plus or minus the direction of V, but it doesn't matter whether we get plus or minus V, because we have V transpose. This minus would cancel out anyway. So here's my simpler formula for V. And what's in the notes. The magic vector that makes this happen. V is equal to X minus alpha E1 over its 2 norm. And the equation on the second, about on the second page of the notes, all come from trying to simplify based on this, just because E1 is such a simple vector. The only thing, but certainly we can use this. The only thing that's missing is I have not told you which alpha we choose. Alpha, we know alpha is plus or minus the 2 norm of X. Is there any reason to choose one over the other? And yes, there is. Because the first element of X minus alpha E1 is going to be X1 minus alpha. Actually, it's just X1 minus alpha. Because the first element of E1 is 1. So here we have a subtraction. Well, we don't like subtraction. Subtractions can lead to catastrophic cancellation. If, like for instance, if X itself, the vector X is nearly E1, these two numbers will be close to each other if they're the same sign. So we want to make sure that this subtraction here is actually an addition. So we set alpha equal, it's one way to do it, would be minus the sign of X1 times the 2 norm of X. So then if we use that up here, that'll be X, the first element would be X1 plus the sign of X1, 2 norm of X. So that way, it's always an addition, not a subtraction. So that will be at least a little safer in terms of floating point arithmetic issues. So Questions about this? Um. Now. So computing a vector B doesn't take much work. And it's an n vector, it takes order n operations to compute it. So what you're doing is you're subtracting something from the first element of x. And in that vector, you normalize it. So computing V is order n flops or floating point operations. Okay. Actually, it's almost exactly n itself, not just order n, but n. So it takes a little work to get the first element, but the VI is equal to XI over 2 alpha V1. I going from 2 to n. So computing V1, the first element to V, that takes a little more work. But once you have it, you're just taking the rest of X and dividing it by something. So every element of V, except the first, requires one flop. You're dividing by that. You compute this number once and divide. Okay. So really cheap. What's also efficient is multiplying by P. Because you should never, ever, ever form P explicitly. We also have this command with numerical algebra. You never form the inverse of a matrix explicitly. So here too is another commandment like that. It actually kind of makes sense because P is its own inverse, and I say never form an inverses. So don't form P either. So P times X, that's going to be identity minus 2V transpose X. But if you distribute, I keep doing that, sorry. If you distribute X through all that, all you're doing is you're subtracting something. So you compute this scalar, so that's a dot product. And you scale V by that, and then you subtract that from X. So this takes roughly 4n flops. So matrix vector multiplication normally is order n squared for an n by n matrix and an n vector. But now it's an order of magnitude less because it's just this rank one update. So since you're not forming P ever, as far as storage, it's enough to store V, because if you have V, you know what P is, and you can apply it. Okay. So now that we have a handle on getting a household reflection. How do we do QR factorization using householder? So I can let A superscript 1 be equal to the original A. And then I'll write A1 as a column partition. So each one of these vectors are the columns of A1.
Is like the first iteration of doing it.
Yeah, because I'm going to be using this notation to identify each version of A
Okay.
as we work on it. Okay. Okay. Now. Okay, we'll go what I do with my notation here. Oh, okay. Oh, right. Ugh, it's kind of messy, but, all right, so. So the vector X that I want to reduce to E1 is going to be the first column of A1. And we choose B so that our first householder reflection, we'll call H1 identity. Oh, I'm going to call this V1. That's my first householder reflection. And I want H1 applied to this vector X to be a multiple of E1. So I'm going to wipe out all entries except the first. So. And the thing is, I have to. I'll find a new matrix called A2. That is H1 applied to A1. And what we get is first row. It's actually going to be the first row of the R matrix that we're after in our upper triangular form. The rest of the first column is 0. And then the rest of the matrix, we have A2 up to A. All right, so I can use superscript 2 for the rest of these columns, but we're only looking at entries 2 to M, column 2 up to column N. So that fills the rest of the matrix. And A is M by N, so that's why we're going from row 2 all the way down to row N. I'm using MATLAB's colon notation to describe what entries we have. So now I'm going to work on this vector here for my second household reflection. Okay. So we're going to choose our household reflection. I'll call it H2 tilde. So that H2 tilde applied to A2, only rows 2 to M, column 2, is equal to, again, a vector with all zeros except for first entry. And that only non-zero entry will be R22. So now if we look back what's happening to A as a whole, my updated matrix A3 will be H2 A2. Now, notice here I have H2 with no tilde, and here I have H2 with a tilde, and that's because they really are different. No tilde H2 is 1, 0, 0, H2 tilde, because H1, the first household reflection, is an M by M matrix. This is not. This is M minus 1 times M minus 1, because it's not touching the first row of a matrix it's being applied to. It's dealing with all other rows. But I also want to describe the overall process as applying M by M matrices to the original A. So because of a 1 here, first row is not touched. Okay. And this matrix is working on all the other rows of A. But in the first column, rows 2 through M were already 0. So it's just mixing zeros around. So it's still 0. In the second column, we have R22 up top, all zeros below it. And then the rest of the second row of R has now been formed. And then what remains is columns of A3, entries 3 through M, column 3, 3 through M, column N. So these vectors are what will get operated on next to get us A4, and so on. So we keep working on a smaller portion of the matrix until there's nothing left to eliminate, or until we get all the way to the nth column. Questions about what we have here? That was kind of a mess. The overall process can be described as follows. We start with A, and then we apply H1, H2, up to Hn in that order. And the result of that is, using a notation I have here, the An plus 1 is what is the output of that. But that is our triangular, that's our R. And each M by M householder reflection Hj has this form. It is, we have Hj tilde down here. And we have an identity matrix of size J minus 1 up here. Um. Okay, yeah. So each one of these is m minus j plus one times m minus j plus one. Because it's working on row j down to row m, down to the bottom. So once we do all this, A is equal to QR, and Q is the product of all of these in this order. And you could think of it as I'm multiplying by the inverses of these to move them to the other side, but each H is its own inverse. So that's why I have H is there, H is here. So that's the QR process. Okay. Now, last time, actually at the very beginning of this chapter, talking about least squares in the first place, I stated assumption that A has full column rank. A has n linearly independent columns, and I should make clear that assumption is still in force. So under that assumption, the Q that is produced by the QR factorization has, we can break it down into its columns as follows. So we have two blocks. This is an m by m matrix. So this first part Q1 has n columns, and then Q2 has m minus n columns. Now this is not actually about householder. This is true regardless of what algorithm is used to produce a QR factorization. Okay, that's so the range of Q1 is the same as the range of A. So the columns of Q1 form an orthonormal basis for the range of A. What about range of Q2? That's an orthonormal basis for the orthogonal complement of the range of A, which makes sense because all the columns of Q2 are orthogonal to all the columns of Q1. So this perp simple here meant to denote orthogonal complements. So in general, I'll give a definition of orthogonal complement. I think you may have seen in a linear algebra class. Okay. So we have suppose you have a vector space V. So for example, the vector space could be Rm. And a subspace S of V. The orthogonal complements of S and V is denoted by S perp. It's a perpendicular symbol. All right. It's defined as follows. It consists of all vectors X in V such that they're orthogonal to every vector in S. So every vector in S is orthogonal to every vector in your orthogonal complement of S. I have a comment in the book that in the book in examples, the QR factorization is computed of a certain matrix. In the examples is computed in two different ways. Givens from the last class have been Householder, and what ends up happening. Okay, I don't have to give this notes with me, but the first three columns. Because A is a 5x3 matrix, so the first n columns of Q in both cases turn out to be the same. And then the last two columns of the two different approaches turn out to be different. Even though they form bases from the same space. I know there is a uniqueness result for QR factorization, like before I prove it, the LU decomposition is unique. But for instance, if you do QR factorization, the only way you could even hope to get uniqueness is if you have some convention like requiring that the diagonal entries of R are positive. So if you impose that kind of a condition, you can at least get a uniqueness result for the first n columns of Q. But that uniqueness may not carry over to these other columns. You're dealing with your orthogonal complements. And they're orthogonal to every column of A, but that's the only property they have to satisfy. And plus these columns are orthonormal to orthogonal to each other.
Question.
Yeah.
You said that we could oppose that condition
Yeah.
where the diagonals are positive.
Yeah.
If the diagonals were not positive, could you multiply it by like some scalar or something?
Yeah, you can. You can make them positive. So what you do is if you carry out QR by whatever it means, and if you find out a diagonal entry of R is positive, then what you can do is you can negate that row of R and then negate the corresponding column of Q. So then you still have A equals QR. But just like with Cholesky decomposition, the Cholesky decomposition is unique, provided you impose a condition that all of the diagonal entries of a Cholesky factor G are positive. Because in a Cholesky algorithm, each diagonal entry is the square root of something. And you could choose positive or negative square root. But given we're talking about symmetric positive definite matrices, it seems sheer lunacy to choose a negative square root, but you could. But you don't have uniqueness unless you insist they're positive. Let's see if, well, we don't have much time, but actually I don't have much left either.
This is something I should know, I just don't remember. Oh, okay. So if A is invertible, the QR factorization is unique if you require diagonal entries to be positive. Now, if A is okay. Oh, and actually, the other uniqueness thing is what I said earlier. Under that same assumption about R, this is unique. That's not. It's going to be some orthonormal basis from your orthogonal complement of a range of A, but that's all I can say for sure. Okay. Right. Actually, the only thing I have left is the algorithm, like the pseudocode form. So, like with Givens, we're going to accumulate both Q and R. So initially Q is identity, R is initially A, and you do all your work on R, so that A is not overwritten. Also, like in the Givens case, we work on each column in a loop from left to right. Okay. And we assume the availability of a function called house, whose job it is to you give it a vector and it will produce a vector v from a householder reflection that will reduce that vector to a multiple of E1. So if we look at entries in row J to the bottom, column J of R. So house X produces the vector V so that V is equal to identity minus 2VV transpose over V transpose V. So house does not produce a unit vector necessarily, it doesn't have to. We just have to remember to normalize it. And Px is the multiple of E1. So that's the job of the house function. If I think if there want to be assignments, I might have that posted. I'll check. Okay. So this vector here is not assumed to be a unit vector, but what we do is to account for that, and you define a constant, a scaling factor C, be 2 over V transpose V. So that the household, so that will still be doing this. So that has the effect of normalizing V, just not explicitly. Okay. Then what we do is we apply this householder transformation or reflection to rows J to the bottom, and from column J to N. Okay. So that would be identity minus CVV transpose, all applied to the matrix, but we can just carry it out this way without explicitly forming the household reflection. Minus CVV transpose times this portion of R. Very important point, though. Watch where I parenthesize. I'm going to put this part right here, V transpose times this relevant portion of R in parentheses. The reason why is, if I don't do that, you put it in MATLAB, just like it was written before without these parentheses. MATLAB will carry out VV transpose. It'll form that matrix first. And then take that matrix times this matrix. That'd be a matrix multiplication. That's terribly expensive. Whereas if you do this is a matrix vector multiplication. And then we have vector times a vector transpose. That's an outer product, which MATLAB will do more efficiently. So that's the way to handle that. Make sure that you parameterize your expression in such a way that you're not accidentally causing a matrix multiplication. That's bad. Then this logarithm would take over end of a fourth operations. Yikes. Okay. One thing I could have done a little differently. This same point came up with Gaussian elimination. Here we're working at columns J to N, but we actually know what happens with column J of R. All the entries of the first column of this will be 0, except for the JJ entry. We also know what the JJ entry will be. We could just compute that and put it in there. So I could have gotten away with J plus 1 to N, as long as I set the diagonal entry accordingly. That could save a little bit of work. Now, here I applied a household reflection on the left to update R. Now, kind of like with Gibbons, we apply the household reflection on the right to update Q. And for Q, unlike R, we're going to update all rows and columns J through M. Remember, Q is an M by M matrix. Okay, so that'll be equal to itself minus scaling factor C, Q, or at least a portion of Q. And then I have VV transpose. Okay. Anyone tell me why I did not have to do any extra parenthesizing over here? Yeah, what's the difference between this case and this case? Right, what, Nemo?
Order of operations
Yeah,
that carries out another.
left to right. Matrix times vector, this operation's okay. Then it has a vector times a vector transpose, it's not a product. So there's no danger of carrying out a matrix multiplication is because of the left to rightness. So if it had been associating the other way, then yeah, we'd have a problem. And then we wouldn't have a problem here. Okay, and that's the QR factorization householder style. Although it's not, maybe it'd be necessary to store Q as long as you store the V's of these householder vectors. I mean, that can be added to a fair amount of storage too. But if since Q is an M by M matrix, if so it's best to store these, not Q, if N is much less than M. So if you have relatively few columns compared to the number of rows, because store Q, that's M by M. If you store all the V's, that's M by N. And if you really needed to construct Q, having the householder V's on hand would enable you to do that. But then you can just carry this out at any time. Oh, well, 1 minute passed, but it's also all I have. Well, does it, if anyone has any questions, or you can all go, or.
Thank you, sir.
Yep.